Hello my friends and welcome back to the You Can Do TV channel. The casting process at Navantia's engine factory is a critical part of producing essential engine components, such as engine blocks and cylinder heads. These parts are primarily made from gray and nodular iron, and the foundry has the capacity to cast pieces weighing up to 60 tons. One of the foundry's major strengths lies in its extensive experience, attention to detail, and the use of high-quality materials. The casting process begins with mold preparation, using chemical molding techniques. This involves mixing sand and resin to create solid, compact parts that form the mold. The use of core shooting machines and sand mixers helps to create complex geometries required for these components. The next step is painting the mold, which improves the final surface finish and reduces potential defects during the casting process. Mold assembly is a crucial task, as the placement of different mold elements determines the quality of the final product. Navantia's foundry operates 3 induction furnaces to melt gray and nodular iron, ensuring precise control over the material properties. A small laboratory near the furnace tests the thermal characteristics and chemical composition of the material to ensure quality. After the casting is complete and the part is removed from the mold, the pieces undergo heat treatment to enhance their mechanical properties and prevent future defects. This step is essential to extend the service life of the components. These parts undergo various machining operations to ensure they meet the required specifications for performance and durability. Key machining processes include milling, turning, drilling, and honing. Milling is used to create flat surfaces, such as the top of the engine block, while turning shapes cylindrical components like the crankshaft. Drilling is essential for making holes for bolts, oil passages, and coolant channels. Honing, typically applied to cylinder bores, ensures smooth, precise surfaces that reduce friction and wear. High-precision CNC machines are often employed in diesel engine machining to achieve tight tolerances. This guarantees that all components fit and function together seamlessly, ensuring efficient operation, reduced emissions, and longer engine life. The 3D rudder blade project represents an innovative step forward in the naval sector, incorporating additive manufacturing technologies. This new design and construction strategy aims to enhance efficiency and performance by combining traditional techniques with modern advancements. A key feature of this project is the use of 17 polymeric pieces, printed in acrylonitrile styrene acrylate, each weighing up to 130 kilograms. These elements play a vital role in reducing manufacturing complexity. The process involves integrating a fiberglass intermediate coating, which adds durability and strength to the structure. Despite its lightweight polymer components, the total weight of the rudder blade is approximately 3,500 kilograms, showcasing a robust design. The blade itself stands about 4 meters tall and nearly 3 meters wide, making it suitable for large naval vessels, such as corvettes. This hybrid rudder blade, created through additive manufacturing, marks the first full-scale prototype of its kind. By drawing on resources and technologies from other industries, This approach opens new possibilities for the naval sector, particularly in the design and fabrication of large, complex components. The combination of advanced materials and 3D printing with traditional methods not only simplifies the manufacturing process but also promises to improve overall performance and durability in marine applications. In this section, we will visit the foundry of Kamihara Steel Casting, Japan. It is a manufacturer of cast steel products for ships and the only manufacturer of 40-ton class products in Shikoku. This is a rudder horn, weighs as much as 43 tons. It is a cast steel product providing support for the rudder blade and minimizes the bending moment in the rudder stock. This will pass the shaft of the screw through the hole in the propeller posco. Pre-swirl vane is an auxiliary hardware used to increase ship propulsive performance. It is located immediately ahead of the propeller and function by inducing tangential or rotational velocities into the flow field of the propeller. Now we will learn the manufacturing process of the ship's mentioned components. The production process starts with making a mold. Special sand is spread and fixed. The work of melting the high iron and pouring it into the mold is done in 8 steps. A giant electric furnace is used for this process. Ingredients such as manganese and silicon are added. Steel is melted in an electric furnace for approximately 4 hours at 1600. The molten steel is then poured into the mold. After the casting has cooled, it is removed from the mold and the excess parts are cut off. Products are inspected in a variety of ways. Inspections to measure stickiness and strength, and dimensional inspections. Products that pass the inspection undergo the final finishing work. Polished by a grinder and using a large machining center. Machining is done. Products made through many processes and inspections are mainly. They are shipped to shipyards and play their role as parts of large ships. Steel plates, approximately 2 to 3 inch, 5.1 to 7.6 centimeters thick, are obtained from steel manufacturers. These plates are cut to the proper size. The steel plates are then bent by large bending machines or hot forming methods. The curved plates then are welded together by hand to form a section of the hull. Large sheets of steel are rolled and welded into the shape of the inner and outer hulls. The section is lifted by a crane and placed next to another section. The welded sections are strengthened by welding curved, T-shaped steel ribs around them. The two sections are rolled slowly under an automatic welder, which seals them together. The rotating sections move beneath the welder several times, resulting in an extremely strong seam. Every aspect of manufacture is checked by inspection and quality control measures. For example, welded steel components are inspected with X-rays. Pipes are filled with helium in order to check for leaks. Once completed, the submarine is loaded onto a dedicated transport vehicle to be transported to the dock where it is launched. The construction of the Spanish submarine S-81 Isaac Perel, the first unit of the S-80 Plus class submarines, represents a significant milestone for Spain's defense and shipbuilding industries. Built by Navantia at the Cartagena shipyard, this advanced submarine showcases Spain's capability to design and manufacture modern naval vessels with cutting-edge technology. The launching of the S-81 Isaac Perel, marked the end of one critical phase and the beginning of the next step in preparing the submarine for active service. This launch took place on April 22, 2021, in a ceremony attended by King Felipe VI and Princess Leonor, signaling the importance of the event to the country. The electric motor, MEP, installed on the S-81 Plus submarine represents a significant technological advancement in submarine design. Developed by Canteri, a subsidiary of the Spanish multinational Gamesa, this motor is 20% lighter than the one used in Scorpene-class submarines. One of its key features is an extremely low acoustic signature, making it more difficult to detect, a critical advantage for stealth operations. Additionally, the motor has twice the shock resistance compared to similar models, enhancing its durability in harsh underwater environments. Another remarkable feature is its ability to provide maximum power continuously without interruption. This results in a specific output 50% greater than that of other submarines operating under the same conditions, making it highly efficient in demanding scenarios. Navantia's Cartagena Shipyard fitted this innovative motor onto the S-81 Plus submarine as part of a broader contract to build 4 S-80 submarines for the Spanish Navy. The motor was mounted in Section 1, a significant milestone in the outfitting stage of the submarine's construction. Over the coming months, additional equipment will be installed, eventually allowing the submarine's sections to be joined, leading to its launch. Next is the installation of diesel engines on the submarine. These diesel engines, produced by Navantia's Cartagena Motors factory under an MTU license, play a vital role in the submarine's hybrid propulsion system. This system consists of both diesel-electric and air-independent propulsion (AIP) technologies, allowing the submarine to operate efficiently both on the surface and underwater. The S-81 is equipped with diesel engines featuring diesel alternator rectifiers, DAR, which provide power in two key ways: by charging the submarine's batteries or by directly supplying energy to the main electric motor. This flexibility is crucial for ensuring the vessel's endurance and operational capabilities during long missions at sea. The engines are designed to ensure high reliability and energy efficiency, as well as to minimize the noise signature, which is essential for stealth operations. The actual process of installing the diesel engines on the Isaac Peril involves precise engineering and alignment to integrate the propulsion components with the submarine's complex systems. This phase of construction is meticulously planned and executed to meet stringent naval standards, ensuring that the engines are securely mounted and that all related systems, such as fuel supply, exhaust, cooling, and electrical connections, function optimally. The S-81 achieved a major milestone when its diesel engines were successfully started at Navantia's Cartagena Shipyard. This engine startup is part of a series of rigorous tests designed to verify the readiness of the submarine systems, as per the S-80 program's systems engineering process. It follows earlier milestones, such as the shipment of the batteries to the vessel and its launching. Construction and final hull closure. The construction of the S-81 began with assembling the pressure-resistant hull, a vital component for the submarine's integrity and operational safety underwater. The hull is composed of several sections, with the final step being the assembly of the last hull segment. This final closure marks the structural completion of the submarine. The hull is designed to withstand the immense pressures encountered at deep sea levels, and the union of the last hull section signifies the near completion of the structural framework of the vessel. At this point, workers meticulously carried out several essential tasks, including califates, or caulking, to ensure that all seams and joints were properly sealed to prevent leaks. Once this process was complete, the hull was welded together using specialized techniques to guarantee strength and durability. Welding the final sections required precision and skill, as it is crucial for ensuring the submarine's safety and performance. With the hull now fully assembled and the submarine's exterior nearly complete, attention shifted to preparing the submarine for its launch. Technicians performed detailed inspections to verify that all components were securely in place and that the submarine met the required safety and performance standards. The launch of the S-81 Isaac Peril was a momentous event, marked by both technical achievement and national pride. The submarine represents the first of 4 submarines in the S-80 class, which will play a vital role in modernizing the Spanish Navy. The S-80 Plus class submarines are designed to enhance Spain's maritime capabilities and project power in international waters. The S-81 Isaac Peril was launched in the traditional manner of naval vessels, a process that involves placing the submarine into the water for the first time. The submarine was placed in a floating dock on the Wednesday prior to the launch, where it underwent a series of final checks and preparations. This process was critical for ensuring the submarine's safe and successful entry into the water. On the day of the launch, the floating dock was moved to a deeper area of the shipyard known as the trench, which has the necessary depth for flooding. The submarine was carefully submerged by flooding its ballast tanks, allowing it to float on its own. This delicate process required careful coordination between Navantia's personnel and the submarine's crew to ensure that the launch proceeded smoothly and safely. Once the submarine was floating independently, it was towed by tugboats and pushers from the floating dock to the armament dock, where it would undergo further development. At this stage, the submarine had no operational propulsion system, but this would be installed and tested in the following months. The launch of the S-81 Isaac Pearl is not only a significant technical milestone but also an important symbolic event for Spain. Ricardo Dominguez, chairman of Navantia, hailed the launch as a safety milestone in the construction of the submarine and praised the collaboration between Navantia, the Spanish Navy, the Ministry of Defense, and the company's industry partners. This collaboration is crucial for ensuring that Spain remains at the forefront of naval technology and that the country can project its strategic capabilities on the international stage. The event was attended by high-ranking officials from both the military and the government, further highlighting its importance. These included the Secretary of State for Defense, Esperanza Castellero, and various naval officers, such as Admiral Aniceto Rosic Nieto and Vice Admiral Pedro Luis de la Puente Garcia Ganges. The chairwoman of the Sociedad Estatal de Participaciones Industriales, SEPI, Belian Gualda, also attended, underscoring the significance of the submarine to Spain's defense industry. The S-81 Isaac Pearl was christened by Princess Leonor, the Princess of Asturias, in a ceremony presided over by King Felipe VI. This act of christening, a time-honored naval tradition, signified the official launch of the submarine and its readiness to enter the next phase of development. Following its launch, the S-81 Isaac Pearl was moved to the armament dock, where it will undergo harbor trials. These trials are a critical step in the process of preparing the submarine for active service. The trials will involve testing all of the submarine's systems to ensure that they meet operational requirements and safety standards. Key milestones during this phase will include the loading of diesel fuel, battery charging, and the first propulsion test while moored. Harbor trials are expected to continue until early 2022, at which point the submarine will begin sea trials. During sea trials, the submarine will be tested in real-world conditions to evaluate its performance and capabilities. These trials are essential for ensuring that the submarine is fully operational and ready for delivery to the Spanish Navy. The Sea Acceptance Test, SAT, was conducted by Navantia's S-80 project personnel and members of the Navy. The test involved an empty chamber trial of the diver lockout system, verifying the safety mechanisms. Observers witnessed divers exiting the lockout, confirming the system's proper functioning. During the test, the submarine settled on the seabed of the Cartagena Arsenal dock, where various trials with the diver lockout system were conducted. The S-81 smoothly opened its vents and rested gently on the dock's bed, partially revealing its sail and depth rudders. This provided a clear view of the submarine's impressive size and engineering, further demonstrating the capabilities of the latest addition to the Spanish Navy's submarine fleet. This successful test brings the S-81 closer to becoming fully operational, showcasing the advanced technology and precision of the S-80 series. The reduction gear plays a crucial role in turbines by reducing the rotational speed from the high-speed turbine shaft to a lower speed suitable for driving the ship's propellers. Its assembly process begins with the precise alignment and placement of the gear shafts, which must fit seamlessly within the housing to ensure smooth operation. Next, the bearings are installed to support the gear system, minimizing friction and allowing for efficient rotation. Once the gears and shafts are secured, the internal components are lubricated to prevent wear and tear during operation. During the assembly, each gear tooth undergoes careful inspection to ensure optimal meshing, as any imperfections could lead to operational issues. The final stage involves integrating the reduction gear with the rest of the turbine system. This includes bolting the gear casing securely and connecting it to both the turbine shaft and the propeller shaft. Quality control checks, such as rotational tests and vibration analysis, are performed to confirm the proper functioning of the system before it is approved for operation. In this section, we will watch the fantastic time-lapse video of the Braemar ship transformation. They cut the entire ship in half, add some extras, weld it up, and set it back to sea. Braemar arrived at the Blohm plus Voss Repair GmbH shipyard in Hamburg for work to begin on inserting a new midsection into the vessel. The operation to cut the vessel in half was completed after 4 days. The new section was then moved into place and the forward section of the ship connected with the new part. The 102-foot, approximately 31.1 meter, section has created additional accommodation allowing increase of the total passenger capacity from 727 to around 950. Much of these new accommodations will also include balconies, bringing the total number of cabins and suites with verandas to 70, including the owner's suite. The greatest addition to passenger facilities can be seen on Marquee Deck, Deck 8. Braemar now boasts a new observatory lounge, with magnificent viewing facilities, in common with her sister ships Balmoral, Boudica and Black Watch. Navantia, with over 250 years of leadership in technology, is not merely preparing for the future, it is actively building it. With an unwavering commitment to innovation and a robust network of strategic partnerships and alliances, Navantia has developed some of the world's most advanced naval capabilities. Today, It integrates, builds, and exports complex naval ships and products, including Aegis frigates and destroyers. Through extensive experience managing complex programs for navies around the world, including those of Spain, the US, Australia, and Norway, Navantia has established itself as a trusted global player. Central to Navantia's operations are two key innovations: T1, the custom-built integrated business management system, and Puma, the shipyard unification model project. These systems, designed from real-world experiences, streamline shipyard operations, improve efficiency, and ensure precise control over complex projects. Both T1 and Puma have been integrated into Australia's SEA 1654 program, demonstrating their operational value in managing shipyard projects, enhancing efficiency, and maintaining strict oversight of programs and facilities. This commitment to operational excellence allows Navantia to deliver high-quality naval solutions on time and within budget. The most ambitious of Navantia's current initiatives is Shipyard 4.0, a visionary program shaping the future of shipbuilding. Grounded in the principles of Industry 4.0, Shipyard 4.0 aims to revolutionize naval production through digital transformation. Navantia plays a leading role in driving Industry 4.0 in Spain and Europe, working in close collaboration with universities, governments, and institutions across the European Union. Together, they promote Industry 4.0 requirements among partners and subcontractors in the naval industry, ensuring that this transformation is not just a corporate endeavor, but a broader European mission. Shipyard 4.0 stands at the forefront of Europe's shipbuilding evolution, creating collaborative environments and ecosystems driven by a more agile innovation model. This initiative also contributes significantly to workforce training and modernization, as Navantia incorporates 13 key digital technologies into its processes and ships. By integrating the shop floor and office floor, Shipyard 4.0 enables full operational intelligence, keeping people at the center of the transformation. At the heart of this initiative is the creation of intelligent shipyards, where suppliers, customers, and production phases are seamlessly connected through a common digital thread. Decentralized systems and cyber-physical infrastructures are utilized, alongside autonomous systems, cobots, AGVs, and drones, enhancing both worker safety and transparency for customers. These advanced technologies pave the way for the design and construction of wireless, connected, and self-repairing ships with enhanced performance capabilities, longer lifespans through predictive maintenance, and improved navigation and weapon systems.